Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin with lecture 18 from the course, but make sure you have watched the previous ones before viewing this one. In the last lecture, we started a discussion on an important topic, the deBROGLIE concept. I hope what all we have discussed in the last lecture that is clear to you. In this lecture, we would continue our discussion and then we would be applying all the concept onto some numericals, and I hope this is going to be an interesting journey for you. So in the last lecture, we discussed that deBroglie said that all material particles in motion, they possess wave character. That means the electrons, they also have a dual nature, but this was what he proposed. And in science, we have to justify everything. We have to give a proof for everything. So what is the justification for the dual nature of electrons? Let us see. First, let us see the particle-like behavior. So this is clear from the scintillations produced. I hope you remember the cathode ray tube experiment where a scintillation is produced when an electron strikes a plate coated with zinc sulfide, right? I hope you remember that. And now one scintillation spot is produced by one electron. This means that a wave-like scintillation is not being produced. It is a particle. That is why only one scintillation spot per electron. Another fact that shows the particle nature of the electrons is the photoelectric effect. But what about the wave-like nature? So this was proved by two scientists who did an electron diffraction experiment. And in this experiment, they took a tungsten filament and they heated it to a very high temperature so that an electron beam was produced. And this electron beam, this was subjected to an electric field so as to accelerate the electrons. Then they were made to fall on a nickel crystal surface, and this caused the scattering of the electrons. And this scattering electrons, they produced a pattern of bright and dark rings on the photographic plate. So this is the diffraction pattern of the electrons, and this was seen that it was similar to the diffraction pattern being produced by X-rays, and hence proving the wave nature of the electrons, right? So I hope you understand, although this is not very important as far as your competitive exams are concerned, but you should know certain things, and this is one important thing that proves the wave nature of the electrons, just authenticating the deBroglie equation. Now another diffraction experiment was performed by G.P. Thomson in the year 1928 by passing electron beam through thin gold foil, leading to the formation of diffraction pattern again like that was produced by the nickel crystals, and this confirms the wave nature of electrons. And the wavelength of the electrons, which was determined by the diffraction experiments, this was in agreement with those predicted by the deBroglie relationship, again proving deBroglie to be right. Now, where do we apply this deBroglie concept? Well, this was applied in the manufacturing of the electron microscope. The electron microscope is based on the wave-like behavior of electrons, just like an ordinary microscope utilizes the wave nature of light. And an electron microscope, this is very powerful a tool in the modern scientific research because the magnification it can achieve is awesome, right? So it can magnify to about 15 million times as compared to an ordinary microscope. So you can understand how much magnification there can be, and it is going to really give an in-depth study of anything. The wave nature of the electron, this has also been used in studying the surface structure of solids. So hence the de-Broglie concept became very important. But there was a limitation to the de-Broglie concept, and you know all this now. Why? Because you remember I told you that it is only valid for the microscopic objects. Because the large objects, they have large masses and hence small wavelength, because lambda, that is inversely proportional to mass, right? So this is something important for you to remember, that the de-Broglie concept is only valid for microscopic objects. Now, this is one topic which is going to be really very important for you. This is going to help you solve your numerical questions. So please do be very attentive. The topic on this slide we are discussing is the de-Broglie wavelength for a charge accelerated through a potential difference. So let a charge Q be accelerated through a potential difference of V. So the energy, that is the potential, electric potential energy, when the charge is accelerated through the potential difference, this is going to get converted into kinetic energy, and kinetic energy is half mv square. So we have half mv square to be equal to Q into V. Q is the charge and V is the potential difference. And I hope you understand this, otherwise you will be able to appreciate when you study this more in physics. Now, if we consider this to be true, which is actually, so we have half mv square equal to Q into V. 2 you take to the other side, multiply both sides by m, you will get m square V square is equal to 2qmv. Okay, and we can say that mv is under root of 2q mv, and mv is nothing but momentum. So we have a very important relationship between the momentum, the mass, the velocity of the charged particle, and the potential to which it can be accelerated. Fine. So this is going to be a very important equation for you. Next, what we have is that we have the de-Broglie equation, lambda is equal to h over mv. We can write mv as h over lambda, and now mv over here and mv over here. So we can equate the both equations, and hence we get lambda to be h over under root of 2 qmv. Fine. So this again becomes a very important relation for you to remember, the relation between the lambda and the potential difference. Okay, so you have to remember this also. You can derive all this, but this will take time. So you have to understand all this, and simultaneously you should remember these relations so that you'll take less time while doing your questions, and there the time is going to be really very important. Now, from the equation 18.1, again you can calculate the value of V also, the velocity of that charge. So we have V to be under root of 2q into the potential difference divided by m, right? And lambda, you can also appreciate it in terms of kinetic energy. How? Let me tell you. We have Q into V. Q into V is coming as half mv square. Half mv square is nothing but kinetic energy. So we will replace this QV by kinetic energy in this equation, right? So we get lambda is equal to h over under root of 2 kinetic energy into mass, right? Another important relation for you to remember. Okay, so that is why I was telling you that the relations I'm going to teach you on this slide, they are very important for you to remember so that you can solve your numericals quickly. Now, if the accelerated particle is an electron with the mass me, then we can substitute certain values in the equation 18.4. We will get lambda to be h over under root of 2 m Over here is becoming the mass of electron. The Q, the charge, that is the charge on electrons. So we are denoting it as E, and V is the potential difference, right? So you know the value of H. You know the value of the mass of electron, you know the value of charge of electron. Calculate it, you will get this as under root of 150 by V Armstrong, or it is 12.3 approximately by under root V Armstrong. So if you know this, you are going to calculate the wavelength if you know the potential difference, or the potential difference if you know the wavelength, very quickly. That is going to be in fraction of a second. So I hope this will really help you. So please do remember them and keep on revising such things. Now something just out of the box and interesting. Can atoms be seen or photographed? Well, the existence of the atoms, this has been postulated for the last 200 years, but it is only recently that it has been photographed using scanning tunneling microscopy, which in short is called as STM. And then, have you ever thought how an electron looks like? Well, I have, but I did not get an answer because electrons, they are too small to be seen even with a powerful microscope. These can, however, be just imagined to look like very tiny dots executing wave-like motion with the velocity of light. Interesting, I hope. Maybe one of you can invent something and let us be able to see an electron. Okay, now there is something we've been talking all about: particle wave, electromagnetic waves, matter waves. So let us understand them and differentiate between what is a particle and a wave. First of all, we have a particle to be localized in space, whereas wave is spread out in space. Then two particles, they cannot occupy the same position in space at the same time, while two or more waves, they can exist in the same region of space. Different particles, when present in the region, they do not interfere with each other, and the sum is equal to the number of individual particles. With waves, two or more waves, when present together, they interfere with each other. That is, the resultant wave can be larger or smaller than the individual waves, right? Next, I have one more difference for you: the electromagnetic waves and the matter waves. So such things, I think they will help you in attempting your subjective questions also, and plus this is going to clarify your concepts even better. So we have electromagnetic waves to be having electric and magnetic fields perpendicular to each other associated with them, while the matter waves, they have no electric or magnetic fields associated with them. The electromagnetic waves can penetrate through vacuum, they can travel in vacuum, whereas the matter waves, they do need a medium to travel. They cannot travel in vacuum. Then the electromagnetic waves travel with the velocity of light, whereas the matter waves, the velocity is going to be less than that of light and depends upon the material particle. The electromagnetic wavelengths of the waves, they are measurable and hence significant, whereas the matter waves we've just now studied of large objects, they have no physical significance because the wavelengths are too small to be measured. The electromagnetic waves, they are actually emitted by a source, and you have studied all about. And the matter waves, they are associated with the particles and not emitted from any source, right? And then we have finally the electromagnetic waves. They are large wavelengths, and the wavelength is given by C over nu. Right, mu the frequency, C the velocity of light. So this is valid for the electromagnetic waves, whereas the matter waves, they have shorter wavelengths and they are given by the deBroglie equation, lambda is equal to h over mv. So I hope you can now understand what wavelength are you going to apply to what question. When we are talking about the electromagnetic waves, your relationship that you're going to use is lambda is equal to C by nu, Okay, while when we are talking about matter waves, the wavelength formula that you will be using is h over mv, right? Many students, they get confused while doing the questions that what is the formula that has to be applied, right? So I hope now this is clear to you. For the electromagnetic waves, you are going to use this formula. For the matter waves, you are going to use the deBroglie equation. So now let us finish the concept with a few numericals based on the concept. The first question says that two particles x and y, they are in motion. If the wavelength associated with the particle x is 4 into 10 power minus 8 meter, calculate the wavelength associated with particle y if its momentum is half of x. So according to the deBroglie equation, we have lambda x to be h over px and lambda y equal to h over py, right? So just dividing the first equation by the second, you get lambda x over lambda y is equal to py over px, and you are given that py is half of px. So you get lambda x over lambda y to be 1 by 2, or you can say that lambda y is 2 of lambda x, and the value of the wavelength of the particle x is given to be 4 into 10 power minus 8 meter. So put it over here, you get the wavelength of y particle to be 8 into 10 power minus 8 meter. So a very simple question. The questions on the deBroglie equation, they are really simple ones. Only the thing is that please do understand your concepts very well. So the next question we have is an electron beam that can undergo diffraction by crystals, and through what potential should a beam of electrons be accelerated so that its wavelength becomes equal to 1 angstrom, right? So we have been given the wavelength and we have to find the potential. You have been told this relation while we were deriving this. So the lambda for the electron is going to be 12.3 divided by under root of the potential in angstrom, right? I hope you remember, we just now did this. Okay, now how we have got it, I'll quickly revise that again with you so that the concept becomes strong. Otherwise, as far as the question is concerned, you can put directly the value of lambda to be 1 angstrom and calculate the potential. Okay, so let me just tell you once again, we have an electron for which the kinetic energy half mv square, this is equal to ev, and lambda, this is equal to h over mv, the momentum. Fine. What we are going to do over here is, what is the value of v in this deBroglie equation? That is going to be h over m lambda, and we are going to put this h over m lambda, the value of velocity, in half mv square. Replace this v by that. What do we get is half m into h by m lambda whole square. This is going to be ev. Fine. So you can calculate the potential from here. V and E is going to go to the denominator side. So we have V, the potential, that is going to be half into h square by m e lambda square. All these values, they are known to you, h, m, e, and lambda, this is given to you. So you will just put that in the equation and you will get the potential to be 150.40 volt. Okay, and if you calculate it by this formula, this is going to come approximately to 151 something volt. Okay, so if it is a multiple choice question, then you can put this formula and get your answer. This is going to really help you a lot. As far as the subjective questions are concerned, you will have to follow this procedure. I hope this is clear to you people. So now the third question we have is that which of the following should be the wavelength of an electron if its mass is 9.1 into 10 power minus 31 kg and its velocity is 1/10 that of light, and the value of H is 6.6252 into 10 power minus 34 joules second. So what do we have over here is that we are given the mass, we are given the velocity, we are given even the value of H. We have to find the wavelength of the electron, and that is given to us by the de-Broglie relation. So we have mass, we have velocity. Velocity is given to be 1/10 that of light. So this will be 1/10 into 3 into 10 power 8 meter per second, making it 3 into 10 power 7 meter per second. Right? And H also is given to you. The de-Broglie relation, just simple value putting, lambda is equal to H over m. We put the values, you will get the answer to 2.426 into 10 power minus 10 meter. So again, the concept, I hope it is clear to you. The numericals, they are very simple if you know the concept very well. Right? I hope you have a nice time understanding the concept. There is no doubt at all in this concept. So that would be all for this lecture. In the next lecture, we would be discussing about the Heisenberg's uncertainty principle. Please do click on the like link to motivate me further to prepare more lectures for you, more courses for you. That is only that can help me work more. So please do click on the like link. Also do subscribe to the channel H2O, and please do not forget to click on the bell icon to get a notification as and when we put up a new lecture for you, a new course for you. If having any difficulty of any sort in chemistry, in this course, in this lecture, please do mail us at h2ochemistry@gmail.com. We'll be glad to help you all. So bye for now. We will meet again for lecture 19. Have a nice time. Enjoy yourself. God bless you.